So Dr. Rakesh Mato joined Cal State Fullerton in the fall of 2016 as an assistant professor. In 2019, he received the Faculty Advisor of Distinction and Outstanding Faculty Teaching Award, respectively. His research interests include photovoltaics, design applications of FPGAs, and some of you know what that is, low power design, mixed signal system design, hardware security, and RF electronics. So, with pleasure, I'd like to hand this program over to Dr. Mato.
Thank you so much for the kind introduction. So let me just share my slide. Okay, so today I'm going to be talking about the challenges, and I will say challenges as an opportunity in computer hardware. So initially I will talk about the exponential growth happening in the semiconductor industry. So with the growth, there were also many challenges, an issue which was happening with this growth. So I will briefly talk about them. And then later on, like I'm going to be talking about what I am doing as a faculty at Cal State Fullerton to train Cal State Fullerton students, and the research work which I'm currently doing in this direction in the semiconductor industry, and some work in progress. All right. So let me get started. So like if this is a simple iPhone, so if I open the phone, so this what you are seeing on the screen, this is a PCB board. And if I look into the PCB board, then the black things you are seeing in here, we call that thing as integrated circuit. So I basically, so I'm going to be talking about these black chips we call, or integrated circuit, we say, I'm going to be talking about them. So this is the first, so let me get started with the history of the computer, which gonna be by which I can showcase what the progress happened in the semiconductor industry. So this is the first computer. This was the first computer built. So like you can see that it's reside in the whole room, and even though it's so big, it can do 33 integer multiplication per second, and like in the computer, to make it operate, some manual wire changing is required. And the mostly, like unlike the programs which used to reside in the memory, in old days the program used to reside in the wire, and someone has to change the wire every time they want to use the computer. So that was the initial computer. Then came this one in 1971, and the smallest printable size in this technology was 10 micrometer, and the total number of transistors on this chip in this microprocessor was 2,300 transistor, and the maximum operating frequency was 1 megahertz. And then the computer progressed further. In 1981, this is another Intel chip. It has 29,000 transistors. This is another computer processor by Intel again in 2004, and it has 125 million transistors. So that's the amount of progress happened in the integrated circuit, in the computer processor. So how it happened? So one of the founder member of the Intel named Golden Moore. So he made this prediction, which is according to his prediction that every 2 years the total number of transistors in an integrated circuit will get doubled. And fortunately enough, Intel continued to follow that trend, that every 2 years the total number of transistors definitely got double in the integrated circuit. So this is the trend. And then all the semiconductor industry followed. Semiconductor companies operating in the area followed that trend. And every 2 years, the total number of transistors got doubled. So So like if I apply the same amount of progress happening in an integrated circuit into a travel industry, so let's say if I want to go from one point to another point in 1978, if it would have costed $900 and the travel time was around 7 hours, and if I apply the same kind of improvement I shown you earlier in the semiconductor, if I apply that to the travel one, the same distant travel cost going to be 1 cent, and the approximately travel time going to be 1/4 of a second. So that's the kind of improvement in uh, that's the kind of exponential growth we saw in the semiconductor industry. And so like Moore's law was not always accurate. So Moore also predicted that uh, the the so the wafer size of like in which the chips are being manufactured, so he said the wafer size going to be incremented to 57, but unfortunately it didn't happen. And once again, like this is the increase in the die size of the chips. Remember that black chips which we saw was in square shape, so that is that die size it's showing over the years. And this is the increase the frequency. So over the years, when we progress in the integrating more and more transistors on an integrated circuit, similarly over the year the operating frequency of the chip also increase. So from 0.1 megahertz it almost reached to the gigahertz stage right now. And the smallest printable size of an printable size on a chip from 100 micron, which is almost equivalent to the human hair. Now it becomes even smaller than an AIDS virus, and the AIDS virus is around zero point 0.1 micrometer. I can even say that it's even smaller than the COVID-19 virus. So that's the amount of small we can print in semiconductor. So why the semiconductor industry are so much focused on making transistors smaller and smaller? Why they spend so much effort and money in making sure that transistors are smaller? So there are three reasons behind it. So the one reason is the speed. So as we shrink the size of the transistor, we can make it operate at higher frequency. So basically it improves the speed. And also in the same area, we can add more and more transistors. And since we can add more and more transistors, we can add more functions to the design. So we can add more functionality, and also it basically saves the energy. I will be talking about that in a few minutes, how it saves energy. So imagine like if I would have made the iPod in the old technology, which I mentioned in 1971, if I would have made the iPod in that technology of 1971, how the iPod would have looked like. So this tiny iPod would have looked like this. Imagine carrying that around like while driving. So this is the smallest feature size. So right now, the smallest printable size is around 5 nanometers. So all of that is the nanometer. So you can see that every 2 years, the smallest printable size is basically becomes half in every 4 years. So it was 32 in 2010, and by 2014, it becomes 14. And currently in 2020 we are almost at 5 nanometer. And I recently heard that right now um, um, Apple is planning to switch to 3 nanometer technology. That's the smallest printable size. And this is the different fabrication done by according projections. And this is the cross-sectional view of a transistor use currently. So this is for the 22 nanometer, and this is for the 14 nanometer. So let me talk about like how like what is happening in terms of like when we are making transistors smaller and smaller. So let's say this is a cross section of a transistor we use. So let's say this transistor shown in here, it's in 35 nanometer. So how this transistor works is So it has, right now you can see that it has 3 terminals. So one terminal is here, another terminal is here, and another terminal here. So to turn on, to make sure the current flows from across the transistor, I have to apply a voltage in here. So right now the voltage is in the 0, that's why it's not turning on. But when I apply the appropriate voltage, so what happens, that electron channel is formed, and once the electron channel is formed, then the current will start flowing, and uh, the current start flowing and the light turns on. So to turn on and off this uh, transistor in 35 nanometer. Please remember I mentioned that currently we are operating in 5 nanometer. Okay, so let's see how many electrons I need to turn on a given transistors. Okay, so the distance between two silicon atom is 5.43 angstrom. So the distance from the channel is 35 nanometer. So if I compute it, it comes out to be 64 atoms. So I need 64 atoms underneath this terminal to turn on a transistor. And I recently did the computation for 5 nanometer, you just need 10 atoms to turn on a transistor. So that's the amount of small I'm talking about. So because of that, there is a lot of uncertainty happening in here, because the distance between two terminals is so less that even small amount of energy can allow electron to go from here to here, which because of that the leakage happens, which we talk about in a minute. All right, and this is that thickness of, so this is a dielectric thickness. So I'm skipping this one right now. Okay, so what are the benefit of shrinking the size of a transistor? So we can add more and more transistor in the same footprint. Adding more transistor into the same footprint mean having more functionality. Having more functionality in the same footprint basically reduce the cost per function, and also it makes device faster and higher in performance. And as I mentioned to all of you that as we shrink the size of the transistor, to turn on the transistor, the total of number of atoms we require is lesser, becoming lesser. So because of that, the switching energy becomes less to turn on a transistor and turn off a transistor. So all of these benefit we are having because of that. Semiconductor companies were so much focused on making transistors smaller and smaller. Okay, so let's talk about the issues and challenges. So this is the power performance. So like as we moved in like from 1971 to 2000, like what we can see, the power dissipation of the power consumed by the chip is also increasing over the years as we are adding more and more transistors. So let me talk about the power density. So power density is nothing but the power consumed by in particular in cross-sectional area. So if I'm talking right now, so the power density of an integrated circuit made between 90s between 2000 to 2010, it's almost equivalent to the power density of a nuclear reactor, a rocket nozzle, or even on a sun surface. So that's the amount of power density I'm talking about. And if we are not careful, then it can lead to burning of the chip. And this is the power consumption happening across like different Intel chips. So around 2006, the Pentium D processor, the power consumption of that chip was 115 watt. Let me show this number in perspective, like how big this number is. Okay, so this is the power. This is a supply voltage for that technology. So if I want to compute the current, so it's gonna be the power divided by the voltage. So the current comes out to be 96 amperes. So how big this current value is, 96 ampere. So um, so like the fuse we have in our home. So like when we have short circuit in our home, then we have electricity get disconnected. So that trip happens around 15 to 40 amperes. And look at this number and look at this number. 96, almost twice that of this number, twice or thrice of this number, and still the chip function. Even after operating at this much current, the chip we are using in the computer, it still functions. Let me show another example here. Again, I have the power and the chip area in here. If I compute the heat flux, so it's nothing but the power divided by the chip area. So it comes out to be 50 watt per centimeter square. Let me once again show this number into perspective. So the heat flux of the iron is 0.2 watt per centimeter square, and heat flux of a frying pan is 10 watt per centimeter square. So this is almost 5 times that of this number. So that's how big this number is, this 50 watt per centimeter square. All right, so that there are different techniques used to do the heat management. So the proper heat removal system is very expensive. So there are various techniques used in integrated circuit to reduce this heat management, and the best solution is the multi-core processors. That's why, like we saw that after 2000 we have all the computers being multi-core processors. So let's talk about the challenges. So the feature size means the smallest printable size is right now too few atomic layers. So because of that, the transistor behavior become completely uncertain. And then because of lot of uncertainty, there is an increase in the leakage power. So what is leakage power is, let's say I turn off the transistor. So if I'm turning off the transistor, then I assume that no current gonna flow through the transistor. But even though transistor is off, the current, some tiny amount of current still flows through the transistor, and there are billions of transistors. So if I multiply this tiny current by billion of transistor, then this number becomes quite big. So because of that, the leakage power becomes a big challenge right now, and it's become so significant right now. Instead of concerning about the main power consumption, now as a designer we are really worried about controlling this leakage power consumption. Even two of my project which I'm currently working on is to control this leakage power. All right, and then we reach a limit point where there is the performance enhancement reach almost its limit. And then I already talked about the thermal issue. All right, so what are the future? So currently, like there are some other technology coming. So there are spintronics based electronics. One of my colleague is working on this project. And then there is a quantum computing, another option. Then there's a DNA computing, that's also another option. And then there is an optical computing. So all of the different option which is appearing. All right. So like as in here, I'm just trying to show that multi-core processors, how much power a multi-core processor basically can able to save, and then in the performance they are much more superior to the single core. Let me talk about the interconnection. So this is a chip. So I'm showing a cross section of a chip. So if I look at there, so like you can see there are different layers of an integrated circuit. So this is so like I cut the chip and I'm looking at the in front of the chip. So these are different layers of an integrated circuit. And so if I'm looking in the 45 nanometer technology in 2008, so these are the wires which connect different transistor together. So since there are billions of transistors and I'm connecting them with a wire, so so look at the total number of wires we have. So in 2008, there were 150 million wires. In 35 nanometers, there were 300 million wires. In 22 nanometer, there were 600 million wires to connect those billions and trillions of transistors together. And if I connect all the wires together, this is the total length of the wire. And this chip is just barely a couple of centimeters, which I shown you earlier. In that tiny amount of chip, that much the total wire is used. so this wire, since there are a lot of wires there, so we reach a point in here, which I'm trying to show in here, that the power consumption happening in the integrated circuit now, it's more than the power consumption happening in the interconnection. So at the same time, so the delay in the interconnection is now more than the delay in the transistor. So what is delay? So let's say if I'm pressing a switch, and the amount of time it will take, let's say if I'm turning on the switch to turn on the light, so the time it will take when I turn on the switch and the light to turn on, that is the delay. So that delay happening in the gate is, or basically transistor, is much less compared to the delay because of interconnection. So that's the point we are reaching. All right, so what we can see that as we are making transistors smaller and smaller, the interconnection basically slows down the performance of the circuit. It consumes more power. Also, it generates more power, and there is a phenomena called electromigration. So, what is electromigration? So that the interconnection, basically the wire connection between two transistors, are becoming so thinner in terms of cross section, is like when the electrons flows through them. So with the electrons, some atoms of that of that wire goes through with that electron. So because of that, that wire connection becomes thinner and thinner and thinner, and eventually you have an open circuit. Because of that, the current not going to able to flow through that. So that is electromigration. We'll talk about that. So what are the solution for that? So the solution for that is the carbon nanotube. So the carbon nanotube has a very nice property, is that the covalent bond between two atoms in the carbon nanotube is much more higher than the copper we use for interconnection in integrated circuit. So they can be a good alternative. I'll talk about that in more detail in a minute. And then optical interconnection. So in optical interconnection, basically what we do, instead of having any wire connection between two transistors, what if we can send data through some kind of light or laser? So that is optical interconnection. So they are considered as a better option. Or maybe the molecular wires are another option, or spintronics based interconnected system. So these are the options. uh, Looks like a suitable option currently. Now let me talk about what I am doing in this direction to train the Cal State Fullerton student. So basically, like when we are making that integrated circuit, so these 5 steps are involved. So what I am doing is like so my students are helping with me in designing at block level stage system design. um, and then later on, like I'm teaching them in one of the class, this is the circuit simulation, how to do circuit simulation. And then once they are familiar with that, they design the chip. So this is the chip design, which my student gonna be learning in one of the class which I'm teaching every semester. And then once the chip is they have designed, uh, it can be fabricated. And after fabrication, the chip generally looks like this. And this project is being funded by FTC. So my students in my 441 class are doing all these steps in one class, in one semester. Let me talk about the research work which I'm doing. So as I mentioned to all of you, like so in the computer, there is something called cache memory. So uh, so this cache memory, like definitely helps to make a computer run faster. And this cache memory basically is consisted of something called SRAM cell. So and so like what happened that the bigger the cache memory gonna be, the better the performance of the computer gonna be. So over the time, what we can see is that the SRAMs, basically the memory, uh, becomes bigger and bigger. So like this is the integrated circuit. And you can see that more than 50% of the area is taken by the SRAM memory. And the problem is this SRAM, like since it's more than the 50% of the integrated circuit, so let's say I am storing some kind of data in the SRAM. Let's say I'm operating something on the integrated circuit. Even though I'm not reading anything from the SRAM cell, because of the leakage power, even though the transistors are not in use, and there are billions of transistors in here, and if I multiply, if I look at the power consumption of the SRAM cell, it's gonna be almost 60-70% of the total power consumption of this integrated circuit. So I was working with my student to figure out a way to reduce the power consumption across this SRAM cell. Let me show what we are working on. So let's say this is a simple SRAM cell. So I try to make it very simple. So let's say I have a binary number. So binary number means it can have a 2-digit, either 0 or 1. Okay. So let's say I have 2-bit SRAM cell. So 2-bit number. So a 2-bit number can have 4 possibilities. So 00, 01, 1011. Okay, so I can store, if I have 2-bit number, then I can store 4 possible number in my SRAM cell, right? So since I have 2-bit, so I have 4 possibilities. What if I have, instead of binary bit, I have a ternary bit? Ternary bits, basically instead of having 2 bits, I have 3 bits. I mean, 3 different numbers, not bit, 3 different number. So out 3, then it ternary have like 9 different possibilities. Then in the same amount of area, instead of this being a binary, if I make them ternary, then the same amount, the same cell can store more amount of data. So by that, what I can do by creating this kind of ternary bit, in the same amount of area you can see in here, I can store more information, almost 3-4 times of information. So that's what I am working on creating a ternary SRAM cell. In the same footprint, I am planning to store more information. And I am currently working with 2 of my students on 2 different technology to create this kind of ternary SRAM cells. The other um, project which I'm working on, I already published a couple of papers in this direction. So as I mentioned to all of you, is that electromigration effect. So as I was talking, that as the current flows with the electrons, it takes some part of the interconnection metal. So you can see that as the current flown, look at what happened to, instead of having like this, there is a short circuit happening in here. In some cases, it can result in open circuit. So as I mentioned, that the carbon nanotube can be one of the option, but the problem with the carbon nanotube is that it has higher resistance than the copper. So it's not going to able to replace the copper in interconnection. But what if we have a hybrid structure? In that hybrid structure, what if that carbon nanotube basically take the maximum amount of current in the interconnection, and such that the most of the current flows to the carbon nanotube, and the some current goes through the copper, so that the overall the what we call power, the current density of across the copper is less. If the current density of the copper is going to be less, so overall the electromigration across the whole structure going to be less, so that this structure can have copper's uh, advantage of lower resistance and carbon nanotubes resistance to electromigration effect. So I'm working on this project right now. I'm going to be submitting a paper, full paper, I think in next month on this direction. I already published a couple of paper in this direction, and one more I'm going to be submitting next month. These are the results which I have already published. some other research projects. So the other research project I'm working on is creating a new next generation of camera chip. So this is a camera from by Canon. So if I open it further, dissect it. Um, so this is a sensor of CMOS camera. So like how it works is, so these are the pixels. You can see these squares in here. These are the pixels. So like if I look at the circuit, a simple circuit of this pixel, it's looks like this. And so what happens is like how the camera reads. So like first a shutter is pressed, and then across each of the pixel there is a capacitor, and in the capacitor uh, the light shines on this kind of photodiode, and once the light shine, it generates some kind of current, and this current is basically stored across a capacitor, and then it's stored across all the capacitor in each of the pixels, depending on how many pixels you have in your camera chip. And after that, then you read one by one pixel cells, and then you send it for processing. So that's how that CMOS camera chip works. This camera chip basically functions. But the issue happening in here is um, that most of the time we store that whatever electrons are generated based on the photon incidenting on that photodiode in here, we storing across the capacitor, and or we know that capacitor is terrible in leaking out those stored electrons, so they are not very efficient. And to make having a very good dynamic range, we have to make sure that capacitor has to be bigger. But if the capacitor gonna be bigger, then basically the pixel gonna have a higher area. If the pixel a single pixel gonna have higher area, then total number of pixels you gonna have in your CMOS camera gonna be less, right? We don't want that. Um, and then also the problem with the capacitor is leak out some of the charge stored across them. So what if we have a different type of technology for storing that photons, which those electrons which are generated by the photon. So I am working with my students on a new kind of device called MEM resistor. So I'm exploring whether the MEM resistor have a capacity to replace this capacitor and be the future option and creating for the next generation of CMOS camera. I'm hoping that that's going to be the solution. All right, and I am basically done. Thank you so much for listening to me. And if you have any questions, concern, you are more than welcome to ask.
Well, thank you very much, Rakesh. I have to admit that it was a little above my head, but I know there are people in the audience that were fascinated with the information. And we have a question from none other than Joyce Ono. So, Joyce, would you like to ask your question?
I just wondered what spintronics meant. Although I just looked it up on my phone, so I think I answered my question.
So actually, I'm just gonna say I'm not really good with that much spintronics. So it just I just know a little bit about it. So like it functions on the concept that I'm not sure whether it's an electron or proton. I'm not 100% sure because that's not my area of research. So it's works on a principle that I think it's electron. There is one kind of carrier which can be in two states. It can be either zero state or it can be in one state at the same time. And they use that kind of concept. But again, I'm not really good with spintronic. I don't work in that direction, so I have no idea, very less idea.
Thank you. I did look it up, and there are some explanations with diagrams.
Yeah, I'm not really good, but my colleague, like Yubai, like he works in this direction. Even his PhD dissertation was on this topic. Unfortunately, I don't work in this direction.
We'll have to ask your colleague to speak to us.
Yeah, sure, definitely. I'm gonna be more than happy to ask him to do a presentation in this area.
Wonderful, wonderful. I see a hand up from Richard McCammon. Richard.
Thank you. Great presentation. It's clear that you're making the effort to produce smaller and smaller, more powerful circuits.
Yes.
I have two things I'd like to make a comment on. One is because you're doing this with electronic circuitry, does that make it more vulnerable to pulses from interstellar events or um, any source of electromagnetic pulse that can disrupt your best electronic circuitry?
Yes, they do. So because of that, like there are there are like different kinds of layers are basically extra layers are added on the integrated circuit to protect them so from those kind of uh, what for the space application. And also there are some kind of redundancy are added in the circuitry so that in case those photon hit the circuit, so the what we call the reliability of chip is not basically it definitely affect the performance.
Yeah, so the other question I have is more because I'm one of the oldest members here. Your circuitry is, your efforts are to devise circuitry to provide more complex functions to this little thing we call a cell phone. And for seniors, what they need is bigger buttons, fewer options. They're not trying to control the world. They just want to make a phone call.
No, but like with that, like we can add more features in the cell phone. We are
Oh,
making we can make like everything smaller, but at the same time we are making adding more and more features in them.
yeah, the thing is that it's physical simplicity and security in the sense that I don't. I don't want to get into high fluting electronics. I just want to make a simple phone call that's secure and can't be. I don't want my phone hacked.
Yes. So actually, like I just want to say a little bit about that also. So like remember I mentioned that during the talk that there is lot of uncertainty in that the behavior of the transistor as we making transistors smaller and smaller. So now that is becoming a security feature uh, for security hardware based security feature, because each chip has a unique identity, because uh, what is happening is that this uncertainty in the chip is completely random. Since it's completely random, so each chip has its own a signature which is not cannot be replicated by the software. So it, because of this new feature, now we are making it much more secure in future. We call that thing as physically unclonable function. Basically it's not possible to make a clone, and by doing this by using this uncertainty, we are making the chips much more secure. And it's a very hot topic in it's very hot topic currently. We call it hardware security.
Thank you. I would like to know more about DNA, but I've used up my term.
Oh, okay. Yeah,
Oh,
actually.
so there's a Jim Monroe has a hand up, and we have two questions in chat. So Jim, would you like to pose your question?
Yeah, I was interested in when you were talking about 5 nanometer semiconductors and so forth, because
Mhm.
when I read the literature, like in foreign policy and so forth, it seems like the technology competition that we're in vis-a-vis China is these smaller 5 nanometer chips. And two companies claim to build them are Samsung and TMC in Taiwan.
Yes, yes, yeah, exactly, yeah.
And the problem, but when I saw the calculations and stuff you're doing, it seemed impossible to cool these things. So, is there any way to rectify those things? Because I just don't see how these companies are building them. I mean, they're building $20 million factories for them. So something's going on. I don't quite understand it.
Yes, so like so for cooling them, so like uh, for cooling the transistors, so transistors, like we are, that's why you're like, you what you are seeing in the new computers coming, we are using multi-core processor, so by which we can switch off certain part of the circuit, which are certain part of the integrated circuit which are not in use.
Oh,
So by that we can cool it.
that's the trick. Okay. Yeah, because it's a major thing in the technology competition going on in the world right now.
Yes, yeah. Mm-hmm.
The scary part of it is there are two Asian companies, Taiwan and in South Korea. Intel is falling by the wayside, is what I'm reading. But those are non-technical people explaining that. But it's kind of get your attention.
Yes. Mm-hmm. Even that recently, like even that Apple people switched to they quit working with Intel and they switched to TSMC for their M1 chip.
Yeah, TSMC, the Taiwan company, seems to be
Yes.
leading the world.
Yes, exactly. Yeah.
Okay, let's move on. Thank you very much, Jim Monroe. We have another hand up by Jim Monroe. I'd love to do that.
Thank you, Janice.
You're
So,
welcome.
so if you look at the Mars Perseverance rover, which is supposed to land here next month, and you look at its computer architecture, it's got a few processors, but it's got dozens of field programmable gate arrays.
Mm-hmm.
Do a lot of its processing in it. Can you tell a little bit about the trade-offs between using an FPGA versus a processor? And I know their total power consumption is for the devices, for the whole rover, is something like 100 watts, which is about the same as one of our laptops. So there must be some power advantages to the FPGAs.
Yes, so like the FPGA, the nice thing about them is so like you can program that on the field. So let's say you want to change the design little bit. So so I teach 2 courses to program those FPGA board. So basically you can program and add more features in your design in Fly. But like in the integrated circuit, once you build it, unfortunately you can't add any more feature. You have to, if you want to add more feature or make some changes, you have to build another integrated circuit. So because of that, now in most of the processor which are coming, it has some kind of FPGA inbuilt in them, so that you can modify the design a little bit.
Are there power advantages to the FPGA in its architecture?
Unfortunately, not. And
Okay.
means they will be like, I will say, oh, in the FPGA the power consumption gonna be more compared to the integrated circuit. But the nice thing about the FPGA is that they allows you to add you can say adaptability in your design. You can change the design.
Thank you.
Okay, we have a few comments in chat. One is from Ken Luke. He's asking if Cal State Fullerton is doing any research on quantum computers.
Not in my department. I'm not sure about the computer science or electrical engineering.
Okay. And the second question, which I don't know that this is not your expertise, but Paul Delan asks for an overview of the computer engineering program. How many faculty members, how many majors, and how many grad students? And also, is the future bright for the program?
So we have around 10 faculty in our department in the computer engineering program, and we have like right now we don't have any major as of now, but like we are working towards it. Like we are So we don't have any specialization in the computer engineering, but we gonna be soon offering a software major and hardware major in our department. And the grad student right now, it used to be a lot, and then mostly the grad student you were mostly from international student, but recently due to pandemic the total of number of grad students are less. But I'm sure that once the pandemic is gone, then more grad students will start coming with us. And I'll say that the in terms of the future of my department, I'll say it's going to be really bright. So the nice thing about my department is like most of the faculty in our department are really young, and they are all working on some really exciting projects, and then all of are working on different projects. So like if you look at mine, I work in low power circuit design, and I also work on solar cells, and there are other professors, they are working on different areas. So I'll say my department is really active because being the youngest department among the all the various department across the CSUF. So I'll say my department gonna be one of the brightest.
That's great. That's refreshing and exciting.
Yes.
So there's we also have a chat from Joyce, who asks, does Cal State Fullerton have the capability of using the different compounds that could be used to create components of chips?
So like unfortunately, like, for doing that kind of research, like we need some kind of a clean room. So unfortunately we don't have at Cal State Fullerton, but like what like we are doing is like we are planning, like we are submitting research proposals so that our student and faculty can work at the national laboratories like Sandia National Labs and other local research laboratories, so that our student and faculty go there and use their clean room facility to build that kind of chips.
Yeah, I had to unmute myself. One area that I saw, growing when I was working was wide band gap semiconductors.
Yes.
Yeah.
Mm-hmm.
Are you guys working or doing anything with that, or part of your courses?
So not now, but like I am really interested in working is direction. So like as I mentioned to you earlier, is that I also work in solar cells, and now the power industry is looking into wideband transistors for um, power devices. So I am planning to switch to that direction because that's one of my future goals, to work in that direction. And once I get some kind of funding, then definitely we're gonna be offering some courses in that direction.
Yeah, with RF kinds of.
Yes, yeah.
It's
Miss,
really critical. One other comment was, I think what you're doing in building department is really important, because when I look at the technology, and it's artificial intelligence and it's semiconductors, that's what's going to change the world. And,
yes.
this is a really important. You ought to be telling your bosses that they need to up it, because this is really important. Young kids that can do this kind of work was really important.
Yes, I definitely agree with you. That's why like we are offering a lot of courses in that direction, and we are also applying a lot of uh, uh, grants, external grant from the government, so that we can do a lot of research and involve our student in those research, and offer courses in that direction, so that a Cal State student can definitely showcase the world the kind of uh, like the showcase their talent to the rest of the world.
Yeah, and I'm sure you could get a lot of grant money. The government's going to be putting a lot of money into this. So,
Yes.
really encourage you to keep doing what you're doing.
Yes, I am working on RF as well. Even last year only I submitted and a research proposal on RF IDs, and this year I'm going to be submitting some more research proposal. Hopefully, if it gets funded, then I can offer more research project and then offer some courses in that direction.
The government's going to encourage you, so money's available.
Okay.
All right, thank you so much, Jim. And Rakesh, do you have any final words for our audience?
Thank you so much for listening to my talk. And if you have any questions and concern, if you have any further question, please feel free to email me. My email address is on the front page. Let me just go to that. Please reach out to me and I'll be more than happy to answer them. And um, and then I just want to say that my student working at Cal State Fullerton are really very bright. They are looking for the opportunity to showcase their skill, and I'm sure they're gonna make the Orange County proud with their work.
I'm sure they will. Thank you very much, Rakesh. I do have a few reminders. As you hopefully all know, we have 2 eclectic series this semester. We have a Wednesday diversity eclectics, and our next presentation is on February 3rd. It will be the subject Orange County Human Relations, presented by Allison Edwards, who is the CEO of that organization. And she will include in her presentation information about Orange County civil rights, which I think will be very interesting. Then we have our regular eclectic series on Tuesdays at 10 a.m., 2 weeks from today. The next subject will be art theft, looting, and repatriation, presentation by David Floof. And I think that will also be fascinating. So keep those 2 dates on your calendar. Wednesday at 1 o'clock for diversity, and Tuesdays at 10 a.m. So thank you again, Rakesh, and hopefully we'll have you back another time.
Sure. Thank you so much. I'll be more than happy to come again and talk about my research on solar cells. And thank you so much for inviting me.
Great. Thank you very much.
Thank you. Bye-bye.
Bye.